Good morning, good afternoon, good evening. My name is Ken Vartanian from Optimec, and I'd like to welcome you to another in our series of on-demand webinars on 3D printing. Our topic today is the application of lens 3D metal printing for materials research at Washington State University. And this webinar will highlight research data gained over the last 8 years at Washington State. Our guest speaker is Dr. Amit Bandyopadhyay, who is a professor of mechanical and material engineering at Washington State. After the webinar, if you have any questions or comments, you may please use our blog feature on optimec.com, and we will do our best to respond to your questions promptly. For those of you not familiar with Optimec, just as a brief introduction, we're headquartered in Albuquerque, New Mexico, and we have an advanced application lab and new product development center also up in St. Paul, Minnesota. We've been focused on 3D printing since 1997 with two major core technologies. The first is lens, laser engineered net shaping, which is used for 3D printing of high value metals. And the second is aerosol jet technology, which is used for printed electronics. Optimec is a full service equipment manufacturer, meaning that we not only develop and deliver systems to our customers, but we provide application support, installation, and training. We have over 175 systems installed in 15 countries, and we have invested over $30 million in technology and product development over the last 10 years. 35 patents have been issued and 50 more pending. What we'd like you to take away from today's webinar are really a couple of key points. First, there are a variety of 3D printing technologies for metal, and each of these technologies have their own unique advantages. Secondly, that really means that selecting the right 3D technology for your particular application is really a critical first step in your decision-making process. And third, there are a number of key factors that I think you'll hear during the course of this webinar that are important considerations. First, is the processing capability of the 3D printing technology you choose, the variety of materials it can support, and the compositional flexibility offered by the 3D printing technology. Second is processing control. And here we mean processing control both at the macro level in terms of creating the kind of geometric structures you want, and also at the microstructure level in terms of creating the kind of performance you need out of the printed part. And third, I think you'll hear today as well a factor as it relates to not only printing 3D structures fully, but also adding materials to existing structures. We call this hybrid manufacturing, where possibly the base material that you are printing on might have been produced by conventional manufacturing methods. So these are some of the key takeaways. So now it's my honor and privilege to introduce our guest speaker today, Dr. Amit Bandyopadhyay. He is a Herman and Britta Lindholm Endowed Chair Professor at the School of Mechanical and Materials Engineering at Washington State University, and he's also a Fellow of the American Ceramic Society, American Society for Materials, the American Institute for Medical and Biological Engineering, and the American Association for the Advancement of Sciences. His research expertise lies with additive manufacturing of metallic and ceramic materials and their composites toward structural bio and piezoelectronic materials. Professor Bandyopadhyay has published over 240 technical papers, including over 170 journal papers. He holds 9 issued U.S. patents, and another 5 more patent applications are pending. So with that, Dr. Bandyopadhyay.
All right, thank you, Ken, for your nice introduction, and it's a pleasure to share some of our research activities over the last 10 years actually using a lens system from Optomec. Myself, Amit Bandyopadhyay, and other lead investigator, Professor Sushmita Bose. We have a joint group, and I'll talk about the application of lens in materials research at WSU. Ours is in School of Mechanical and Materials Engineering at Washington State University. This is a very basic concept. Because we'll talk about lens and additive manufacturing, I just still would like to share, what is basic additive manufacturing, where you can actually draw something using a CAD and then slice it virtual world in the Z direction, and then take each slice and send it to a fabricator, and basically then use the fabricator to build parts. The parts and prototypes that we build are not specific to any tools or dies or anything like that. So that's the biggest advantage. There is no pre-preparation of making parts. In terms of the cost of the parts, it remains the same whether we build one part or we build 10,000 pieces. Sometimes it's an advantage, sometimes it's not an advantage. If you are looking for low volume applications, this is really a fantastic application. So if you look at a simple example like a hip stem. So normal, engineering, manufacturing, the conventional path, we'll go look at the design, then we'll make the tools and dies first. In this case, if this is a hip stem, we'll go for either forging or investment casting. Both of them are industrially practiced because it's a large volume. And then from there, once the part is forged or cast, you can use it for CNC to make it finished machining and so on, and then go for finished grinding. Sometimes some of these hip stems we like to have it coated. If you're looking for a coated implant, then we will basically add the surface of the porous coating or calcium phosphate coating or whatever we like to have, we do that. If you're trying to do it through the additive manufacturing, fortunately, we don't need to do most of anything. So once we have the CAD file ready, we can basically go and build it, and then depending on the area that we like to have the rough surface, we keep it there. Rest of the surface we finish it. And this is for any standard metal-based additive manufacturing. So though it's an advantageous part, there's one more subtle thing. Sometimes we don't realize it. Because we are building directly from the CAD, if there is any file modification or things like that we need to do, you can do it from between the part 1 and part 2 or part 10 and part 15 or whatever it is. So any modifications can be done very easily, which is a challenge for conventional manufacturing, because if we do any modification in the part design, we need to get back to the tool design and manufacturing steps and so on. Now what are the challenges? The first thing that we need to understand, that every additive manufacturing machine or technique has its own advantages and own challenges. Okay, so it's very important for the user to understand and realize what exactly that they need to do so that they can modify or they can select the specific tool that they need to purchase. Some processes require post-processing. If the particular device are sensitive to that, again, that's a piece of information we should know, because some processes without post-processing we cannot do, others post-processing may not be necessary. Part quality we have improved significantly, okay, but it is still, it depends on what the quality that company is looking for or the user is looking for. So this is still an active research. If it's a microstructure, the additively manufactured microstructures are typically much more finer grains than normal conventionally cast parts. That should be taken into account. The surface finish will be rough. Again, rough is a crude statement. It could be very rough and not so rough, but these are the kind of things we have to make sure we understand before we select a process. And the relative ease of processing is definitely a big thing, but at the same time we also need to realize there is a huge cost to buy or purchase a machine. If somebody is looking for 10 pieces of parts, then they may not need to use or purchase a new machine, but just use the machine. So the ease of processing and cost of machines should be something that we need to put them together in the decision making process. This is a lens machine. We have installed it in our lab in 2005, and since then, fortunately, we are using it non-stop, and it has worked really well. In terms of basic technique, we have a high power laser. Ours is a 500 watt Nd:YAG laser and XY Z controller. XY on the table and the Z, the laser moves. So we can go down to the atmosphere control, 10 ppm or less in oxygen. So we can actually make a variety of materials that are sensitive to oxygen, such as titanium. We can typical feedstock powder size 50 to 150 micron. We have 2 hoppers, so we can actually make 2 different powder mix on the fly if we need, or we can pre-mix it. And essentially what we are doing in a lens is a micro casting. So we are casting we are basically putting the metal at the focal point of the lens, and we are melting the metal. So when we are done melting, we basically use that at that focal point, and then we move the stage. So we have a line of liquid metal that is being solidified, and the next line is put on top of that or side of that. So some of the casting challenges sometimes are real in this process also, but that's inherent with this technique. So a typical fabrication, we have the design, let's say hip stem. We go and create the slices. Once we are done with the slices, we go to the Optomex software and decide all the parameters, motion control and so on, and then we basically run the machine. And a hip stem about 8-inch long, between 2 and 3 hours depending on the other features, it's ready and we can actually manufacture it. This time will depend on what's the laser power, what's the system. So it is not a fixed, but if we have a higher power laser, we can actually run the process faster, and then it may take less time and so on. So I'll talk very briefly about key advantages of lens in terms of many other additive manufacturing technology. The first one is compositional flexibility. If we are looking for making materials with multiple compositions or vary the compositions as we build, there is very few techniques available that can do what lens can do. We can actually do metals, ceramics, composites of metals and ceramics, whether we can do pre-mix or static composition control or dynamic composition control. Either way, we can do that using lens. The second thing is, we talk or we only think, whenever we think of additive manufacturing, controlling the shape. So we can build a part with certain shape. But with techniques like lens, we not only control the macro structure or the shape, we can also control the microstructure. Because we are putting the laser power, and as we deposit, depending on the laser power scan speed, we can actually tailor the microstructure, and inherently we can tailor the properties, mechanical properties of these systems also. So we can do higher power laser, and then we can cool a lot faster, which means we can create finer grain microstructure using the same shape part. So it gives us an idea of how to tailor materials, keeping the shape constant and the macrostructure constant. And the third, which is to us in a really big thing, because we are in a university and we deal with students, we don't need to do a lot of optimization of a variety of parameters. Really 3 parameters that we play with: laser power, scan speed, and powder feed rate. So for us, if we are working with a new material, we like to see what is the laser power minimum we need that can melt, and then from there we can see if we can melt it, then the scan speed, how fast we are going to move the stage, so that the total energy input at the focal point of the laser, that is controlled by that. And then finally the powder feed rate. So you need to imagine the powder feed rate means powder is a cold thing that we are putting it at the hot zone. So if we increase the powder feed rate, that means we are basically slowing down the heat input. If we decrease the powder feed rate, that means we can keep the heat longer in that focal point. So by tailoring these 3 parameters, we can work with most any materials quite quickly to see if we can use the lens process to manufacture some parts using that or not. So this is a my examples that I'm going to talk beyond after this slide will give you some idea. We can actually make compositionally gradient structures. Again, this is unique to processes like lens, where we can actually use a predetermined structure. We can make it out of one material, two material, or we can change the composition dynamically. We can also use lens or using for on-demand coating type of application. In other words, if we have a part, we just want to repair certain areas, or if we have a part, then some areas we want to put a high temperature coating, or if you have a part, some areas like implant, we want to put a bioactive ceramics coating. We can actually do that in a finished product using lens. So whether it's a hard coating to increase the corrosion resistance, high temperature resistance, or soft coating for bioactivity or biocompatibility, that can be done. Obviously, direct fabrication is a key thing for additive manufacturing. We have done in our group, both metals and ceramics. So basically, it's unique. The ceramic processing by ceramic casting, literally melting and casting. So I'll give one example to show we have done variety of materials. And this is also a unique process because it's not a powder bed, it's a powder feeding. So we can actually make porous structures, keeping the open pores not filled with loose powders. So we can actually make direct porous structures with a gradient porosity or uniform porosity, whatever we like, whether it's a metal or ceramic or metal ceramic composites, both. Some of the materials that we have used at WSU, and I'm not going to talk all of them. Tantalum, it melts at over 3000 degrees Celsius. Titanium, obviously many groups they do it, we have done it. Bulk amorphous alloys, I'll talk a couple of slides to show. Inconel, stainless steels. We have also done actually aluminum. It's not easy. In a 500 watt, we have done aluminum with some silicon in it, and that silicon is actually absorbs nickel, zirconium, and composites of many of these systems. In the ceramic side, we have done pure aluminum oxide, lead zirconate titanate or PZT, calcium phosphate, and moon rock regolith or moon rock simulant ceramics here. The point I want to make sure before I head into the next slide and examples, in the lens processing, this one parameter we need to understand very clearly. That is how we can process a ceramic or metal. The two factors that are very important. One is the conductivity of the material that we are dealing with, and the second one is how much heat how much laser power it can absorb. So for a metal like tantalum, it absorbs laser like crazy. So it absorbs so much that in a conventional processing, tantalum processing is very difficult because of such a high melting point. In lens, when you hit with the laser, it's like water. So we can actually build tantalum parts even fairly low laser power, 400 watt or so or less than that, without any problem. In fact, sometimes it vaporizes, it absorbs so much. So because it absorbs the laser and it's a poor conductor. It's the same thing with ceramics, like aluminum oxide, it absorbs the laser and it's a really bad conductor. So as a result, we can melt ceramic like aluminum oxide, lead zirconate titanate, calcium phosphates, and it's, not the calcium phosphate, sorry, aluminum oxide or PZT and moon rock regolith and things like that. So the things that we have to be careful, whenever we look at a material, we need to understand how well it absorbs the laser power and how good or bad conductor. Copper, on the other hand, is such a great conductor. Doesn't matter how well we hit with the laser, we just cannot melt it. So that's the part, once we acknowledge that, it makes life a lot easier to actually build parts using lens. So this is the first example, and we spent really several years, and based on our results, I'll summarize it in nutshell, our activities. We got this machine with an idea that we'll make some of the biomedical devices. This is back in 2003, 2004 when we proposed that in the area of biomedical devices, we will basically make structures that does not have to be completely solid, because that's what the industry uses. We cast or we forge. That means these are completely solid material, titanium, cobalt chrome moly, or stainless steel, and so on. But the challenge is because they're solid metal, when they go as an implant, the stiffness of these materials can have a bad effect on the surrounding bone, because that stiffness difference makes the biomechanical load transfer will be more into the implant, and that can actually make the surrounding bone weaker. So one hypothesis is if there is anything we could do to lower the stiffness of the implant material. There's a lot of research, for example, in the titanium side of it, to use beta titanium alloys, which has a much lower modulus than alpha beta Ti64 alloy. Our hypothesis, if we can use technology like lens, we can actually make porous structures, and where the porosity is only inside. So from outside, you will not see it. Inside, you can have a variety of porosity. So you design in your finite element analysis and decide how much porosity you need, and then you basically make this part with that kind of internal porosity. To give you an idea, all three of them are Ti64 implants. Okay, the top one is solid implant. It weighs 135 grams. The second one is porous implant. It has a structure like this. Okay, it weighs only 82 grams. And the third one is a completely hollow implant. It weighs 60 grams. So looking at it, you will not see it, but we have given these implants in presentations to many people. They will hold it and they'll say, what? There is a significant weight difference. Now if we do look at the effective modulus, because effective modulus means now we are making a composite of the metal and the air, the effective modulus also changes, and you can see it here. So depending on the porosity, if it is a more porous, the modulus goes down, and we can very easily create structures even with titanium and pore that has a modulus similar to the bone, natural bone, human bone. So essentially, with this kind of concept, with this kind of manufacturing technology, if we can club them together, we can make implants which are which should offer a longer implant lifetime than the normal fully dense implants that are currently in the market. This is a nutshell of a variety of porous structures over the years we have worked on, just to give you an idea, from titanium to tantalum to Ti64 to cobalt chrome moly to nitinol. These are all materials that are widely used in biomedical device industry, and the point I want to make is if you look at this bar actually shows that doesn't matter what's the material and what's its density, we can actually bring down the overall modulus of all of this material within the bone. Now we have to look at fatigue resistance and other parameters, so once we do that, maybe we will go a little bit higher than that, but tailoring the modulus using this kind of technology is definitely possible, and it's worth exploring it. And if you look at the basic mechanical deformation, it's just one slide I'm going to show, because whenever we are actually designing porous structures, there are many ways we can actually design porous structures. We can have residual porosity by lowering the lens laser power, by feeding the powder a lot faster, or we can actually design pore volume in a way in the CAD file itself. So this is a papers we published in Philosophical Magazine a few years back to show that the deformation behavior also will be different as we change the pore morphology or porous structures. So what we did is we built random porosity structure and design porosity structures, and then with different load, different time, we actually did a CT scan, micro CT scan, to understand how the pores are deforming as a function of time. So this is a design porosity before we started any loading, and this is after some time, and you can see the deformation is very uniform. Whereas this is a design porosity, this is the pore morphology, this is before we started loading it, and after we started loading it, we can see the structure on the top and bottom are fairly similar, but the cracks are kind of propagating more in the bottom side of it. So again, the failure may be located preferentially some areas in the design porosity structures than in random porosity structure. The point I want to make is whenever we deal with any porous structures, it's very important to understand the mechanical deformation towards any application. We can actually make it, but that sometimes is a painful process because we can make so many different things. The question is what makes sense to make, and that's what we have to be careful about. A simple example, I'll briefly talk. This is a 2-year work. That's just one slide. So this is osseointegrated implant, like your root canal in a dental implant that we can put it here. I can like this. This is very common. About 60 years back, it was not done. Today, everybody kind of knows it. So what dentists they do it? Dental surgeon, they will put a metal stub and let it sit there for maybe 6 weeks to 6 months, and the bone will integrate that, and after that they can put a false tooth on top of that, and this the metal piece will then anchor or hold the tooth. that is missing for a normal patient. So if we can do that, theoretically we should be able to do that in other areas. It does not have to be dental. Theoretically we should be able to do that for whether it's if there's an amputee, whether it's a finger or upper limb or lower limb, we should be able to put a metal implant inside the bone and then let the bone heal and grab the metal implant, and then essentially that person, whenever he or she needs to use it, they can put an external fixture and basically move it, and because the metal piece is already built in there, that will give the senses like, well, whether it's at a heavy load or low load and things like that. So right now for amputees, typically we use a socket fit implant. That's a very common if it's a lower limb. Okay, this is typically what we use. The Brenmark work, put a threaded screw and do that. Here we have shown that we can actually combine the lens type of technology where we can actually do the CT scan image and we can tailor-made these implants, and then basically this is the implant that will be osseointegrated or put inside the bone, and this is an external fixture. Then we can add, like here, this is not our work. This is so this is the implant is placed inside the thumb, and then external fixtures can be done. It is not only giving a better performance, it also encourage or enhance the patient's psychological feeling that I am not anybody different. Okay, so what we have shown in this work that because we can actually do from CT scan image and tailor the implant, we can actually tailor-made the size of the implant depending on the pore cavity, as we placed in a dog cadaver bone. We worked with 20 dog cadaver bones, and we actually did design modifications and variations, and finally showed that we can enhance the mechanical locking significantly by tailor-making these kind of things. Again, this is a simple example. This particular piece of metal implant is porous partially and partially solid. So we can actually tailor the porosity based on where the bone tissue integration or skin integration is needed, and by doing that we can actually make patient meshed implants significantly better. You can find porous metal application variety of things in your area, but this is basically the fundamental concept that can be utilized to make, whether it's a biomedical or aerospace or whatever application. This is also another exciting work we did back in 2006-2007. The paper came out in 2008. We actually built a pure aluminum oxide part using lens. So our feed powder was aluminum oxide, and so high purity aluminum oxide, standard commercial powder. The powder we got was 44 to 74 micron size range, and we use a aluminum oxide substrate, low oxygen pressure. But look at here, the laser power is only 175 watt. So really low end even in our system. Why we need that low end? Again, goes back to the same fundamental science that aluminum oxide is a very poor conductor and absorbs laser like crazy. So we need to make sure we don't put too much laser power, then we will not build anything. So at a very low laser power and scan speed and powder feed rate also we adjusted it, we could build actually parts. These are as processed aluminum oxide parts right out of the lens machine. This is a compression cylinder. We made several of them to test mechanical properties. This is just to show that you can actually build features. These are standard CAD files that are available, and this is a microstructure, cross-sectional microstructure. This is the one layer, this is the second layer, this is the third layer, this is the fourth layer, and so on. What is unique here, you need to realize, and this is, I don't think anybody has done it before, is we are looking at columnar grain structure, which is very typical of cast metallurgy, cast metal structure. But we are actually getting and seeing that columnar structure in ceramics because we are melt casting ceramic. Okay, we don't melt cast ceramics in any, we take the ceramic powder, we sinter it and all these things. Here we are actually melt casting. We're melting the ceramic powder, casting it and building parts. Word of caution, two things. Number one, because it's a ceramic, it has a very poor thermal stress management thing. So if we want to make a big structure out of this type approach, it may not work because of the thermal shock resistance, poor thermal shock resistance of most ceramics, if not all. It will crack. So we are good about, these are about 1 inch size parts. We are good about that size range. Anything beyond that, it's a problem. If it's a layer coating, just pure ceramic coating, we are good there as well. So this technique works very well for small size ceramic parts and so on. The second thing is we are using a oxygen partial pressure level of 10 ppm or less. and we are actually building aluminum oxide. So what we found in our aluminum oxide parts, as we actually build, because of the low oxygen level, the aluminum oxide parts look black, means they are actually low oxygen. So it's not Al2O3, Al2O3 minus delta. So they are oxygen deficient. So that's the reason what we did is we tried to heat treat them at 1000 and 1600 degrees Celsius to really understand if any changes in the properties that can happen. And so if you can look at it, this is the grain size that's at 6.6 micron, and then this is basically as fabricated, and then after 1000 degrees increases a little bit. By the time you are heat treating at 1600, there's a large difference in grain size. Okay, and this is again the build direction, and you can see the columnar grains in polished microstructure, and these are all alpha alumina. So we are not making any phase transition or anything like that. These are pure alpha alumina, which is what we are processing using lens. And if you look at the mechanical properties, the as fabricated one, the hardness is pretty high, 1556. That's what typically we'll get, but there is definitely a sensitivity between longitudinal and transverse direction. And longitudinal is almost half, because these are compression testing. So when you did compression testing, the crack actually pushes, so the longitudinal columnar grains are actually weakness. So we got almost half the strength value for longitudinal than the transverse direction. But once we are done heat treating, we're not changing much in the hardness, 1556 to 1548, almost no change. But at 1600, definitely there is a change, and the difference in there's still difference, but the difference is lower, and you can see the difference from the fracture, fractography. This is the fracture surface of the as processed. This is the 1000 degree heat treatment, and this is 1600. By the time we are heat treating at 1600, there is a lot of sintering we believe is happening. So as a result, all the clear grains that you can see it in the as processed structure, they are gone. There is a nice smooth fracture surface. So again, if we need to do ceramic processing like that, maybe there will be a post-processing heat treatment may be necessary for a composition that you may be interested. This is kind of taking the same thing. This was a fun project for us. We used moon rock simulant or moon rock regolith that we got it from folks in NASA, and then we did the same thing. So again, I believe we showed that in outer space you can have a lens machine, and that can build parts, maybe simple shapes that we do not care much about in here. But if you want to make even a brick or things like that, you're not talking about laser sintering. Again, you're mild casting. Okay, we are basically taking the moon rock regolith, we are melting in and casting it, okay, using laser power. And this is a layered, we build these parts layer wise. Okay, and again, these are not large huge structures, but it shows that it's possible. And this particular composition had a lot of silica, and so you can see the glassy phase. But again, this is possible if we want to do that. We took it a little bit beyond, and we never had a chance to publish this data, but just to see, can we really make use of something, if it happens. So we kind of thought about, okay, what happens if there is a metal piece breaks down in space, outer space? Can we actually join that? So again, these are broken standard titanium pieces, and then what we did is we put some moon rock simulant in our lens system, and we just raster the laser on the joining area, and you can see the stress strain curve. So it actually, so this is the hardness. Sorry, this is the cross sectional hardness, and we looked at the mechanical property also, and it's not going back as much, but we could recover about 70% of the strength value of the original metal piece using that moon rock simulant as a welding material. And again, the question is, why should somebody will use moon rock simulant as a welding material? Sure, I'll argue that's not needed here, but again, this was a hypothetical case. If something breaks down in moon surface, can we just use a laser based technique available there and actually join it and fix it? And answer could be yes, and showed the microstructures here, a lot of glassy phase, but you can actually see that from substrate to moon rock, there is a substrate here, and then the moon rock, there's a nice and smooth transition. So this is from one side to going to the other side. This is also another fun area, but we spent about 3 years or a little more than 3 years working on bulk amorphous alloys. These materials show some very unique properties. These materials, because there is no grain boundary, their corrosion resistance is very good. Their elastic modulus is very high. Elastic deformation strain is also quite high. So they have some unique applications. The question is, can we make it using this kind of processes? Okay. So before I answer that, let's ask what actually is needed. Why these materials are difficult to process? To keep it in amorphous state, you have to cool it so fast so that it never get a chance to crystallize. So in this case, we really need a extremely high cooling rate. Okay. And most normal casting process will never allow us to actually accomplish this kind of cooling rates. Okay. Now this is inherent in lens. Lens, because we go to very high temperature, we can cool things really fast. Okay. And because we are doing microcasting, we don't actually change the composition also. So we felt we should be able to make, bulk amorphous alloy parts using lens pretty easily. So we could accomplish in lens between 10 to the 3 to 10 to the 5 Kelvin per second cooling rate, which is quite challenging for most any system that you can think of. Okay. We don't have a dilution effect because this bulk amorphous alloys chemistry is very complex. As you can see, the chemistry I'll show in the next slide. We can preserve that. Okay. And we can actually in that case make whether bulk shape or coatings or whatever we want. We should be able to do those things. Okay. So what we did is we got commercially available 2 different chemistry, both of them iron based. This is no particular fascination why iron based, it's just what we could get hold of. This particular chemistry does not have niobium, this one has niobium, and we use 3 different substrates. One is stainless steel 316, widely used. So it's already corrosion resistant. We can put bulk amorphous alloy coating or structure and see if we can change that. The second one we work with titanium, and third one we work with zirconium. Again, the whole idea is, can we use bulk amorphous alloy type of material to coat it and improve the corrosion resistance or high temperature properties and so on. This is the result in stainless steel, and again we published this one. We see the actual dilution zone is only 7 micron. That means only 7 micron where bulk amorphous alloy chemistry and the stainless steel chemistry is mixed. So pretty much we can preserve the bulk amorphous alloy coating layer, very nicely in actually the coated samples. That's not a problem at all. So this is our coating. Okay. This is the transition zone, only about 7 micron, and beyond that on right hand side is the bulk amorphous alloy, left hand side is stainless steel. And again, the 250 watt laser power was good enough for us with this particular chemistry. You don't need a whole lot of things. Scan speed and powder feed rates are 20 millimeter per second and 19 grams per minute, and we could build actually bulk structures with this as well. I'll only show this in terms of really go TEM and all these things, but if we look at the high resolution SEM and transmission electron microscopy, we basically preserved the amorphous nature of this composite, of this coating. We did not deteriorate anything. So essentially we have some crystalline pockets. We analyzed the powder. The powders also had the crystalline pocket. So lens processing did not deteriorate anything. It just preserved the entire bulk amorphous nature of this coating. So if we had the 100% pure bulk amorphous powder, I think lens processing will give the product the same way. If we look at it on titanium, this is a coating on titanium. Again, we can see there's some bubbling effect because they are not good conductors, and at the same time they absorb laser so much that we have to lower the laser power. But this is the coating, and this is the titanium substrate underneath. And again, if we heat treat it, we can actually, or laser heat treat with the laser pass, we can vary the how much crystallinity we want or what kind of crystalline shapes we want and things like that. Very basic material science by chain tailoring, structure property relationship, and those are all possible whether we just build it as is or we build it and then blank laser we bring it to heat treat the surface by depending on the properties that we are looking for. Thickness of the coating will depend on whether we are putting 1 layer or 2 layers or 3 layers, depending on the what kind of performance you are looking for. And this is on zirconium. Again, this is not an easy substrate to work with, but we can actually put a bulk amorphous alloy coating on zirconium to show that it can enhance the corrosion resistance significantly. Again, we have coating with a very low dilution zone, very nice thick bulk amorphous alloy, and the properties and microstructure can be tailored based on the laser processing parameters. I'll talk about a couple of examples and then I'll stop. One, those are kind of corrosion resistance. For in the biomedical side, we have many folks have shown, and it's already used in the industry, that if we can put a calcium phosphate coating on metal implants, that can enhance bone tissue integration. Now, question is, well, if we are producing metal implants, can we just bring a final product and actually put a calcium phosphate coating using lens? And that's the hypothesis we had, that yes, we can. And we fed calcium phosphate powder from one of the hoppers, and we were actually doing it on top of a titanium substrate. And you can see when we do that, we can actually have a nice, these are the calcium phosphates on the columnar grains, and then if you look at the outer surface, going to the absolute outer surface equiax grain, and this is the top surface, these are all calcium phosphate pockets, and because it's an etched surface, we have already etched the titanium. So we can actually make a very nice, homogeneous, very strongly adherent, really it's not a coating, it's almost like a titanium to composite of titanium calcium phosphate. We can actually make it. And if you look at the properties, you can see depending on the laser power, we can actually change not only the thickness of the coating, we can also change the hardness of the coating and so on. So we can actually play with these basic lens parameters, and we can show that you can vary the coating properties depending on the hardness or biocompatibility or whatever you want. To show that what happens in terms of basic biocompatibility, this is my titanium control, this is the laser processed, and this is the nanotube or other types of nanotube. So you can see by doing the laser processing between day 5 and day 11, we can actually enhance the bone cell integration on the surface, much better than what it was before. We have done in vivo studies with rats, and we actually showed that the coated samples show much better tissue integration as well. Because of this lens, I didn't want to get into that side of it. And this is the kind of the last slide. This is, everybody wants to build parts. So apart from unique shapes and structures, you can also actually make standard parts. So this was a case study. We basically had this is a patient with fractured skull. This part was missing. So you can actually take from the right side image, you can make the CAD file of the defect site, and it's a cranio facial domain of implant manufacturing. We have used that CAD file, and then built a titanium part out of it, and this is the titanium implant, and the holes were drilled later, not manufactured as. So this is the plastic model of the skull, and this is the implant. And so essentially, apart from making unique features and things like that, lens can also do, in our research, what we have done, standard parts and products using lens. So just to summarize, what we focus on in our research using lens is not just to make a whole bunch of titanium parts and things like that. We really try to focus on parts that are difficult, if not impossible, to make with conventional manufacturing techniques. Okay, so for example, closed and open porous structures. We can design compositionally gradient materials, structurally gradient materials with porosity, and we can make those things. We can make coatings on demand on areas on a pre-existing structure, whether you're talking about repair or you want to improve the performance of corrosion or high temperature, we can do that. We can innovate new materials. If we don't know exactly what chemistry to use, we can use 2 different materials, and we can vary the chemistry on the fly or predetermined, and then basically we make a variety of materials, and we basically improve. We can test and see which one will give us the best performance. And the last one I did not touch, but very recently we have shown that we can actually utilize self-propagating high temperature synthesis to make unique materials in lens. A simple example, for example, if we think of titanium diboride, it's very difficult to process, but using lens we can feed titanium from one hopper, boron nitride from the other hopper, and as we process, we actually create the reaction and make titanium diboride and make titanium diboride or titanium nitride coatings on top of the surface of the sample. These things are almost impossible to do using any standard manufacturing techniques. In the world of materials, this is really quite unique. And so I like to acknowledge, obviously Dr. W.M. Keck Foundation is what helped us to get the machine here. Their support is greatly acknowledged. For the research, we are blessed with funding from NIH, NSF, ONR, And MG Marduk Charitable Trust also helped us in terms of acquiring the other machines and some part of lens as well. For different personnel over the years worked, a few names I should acknowledge. Dr. Bala, he was a research associate. He is now at CGCRI India. And various graduate students, current and past, and undergraduate students worked with lens and make all the results that I'm showing here possible. Thank you.
Thank you very much, Dr. Pandeyopathy, for that enlightening presentation. We'd like to conclude with just a few commercial notes. Again, for those of you who are not familiar, Optomec offers a variety of 3D printers that are really suited for different end-user requirements. On the lens side, we have three different products or systems that we sell. The Lens 450 is particularly targeted to R&D customers in the academic community. The Lens MR7, which is meant more for materials research and rapid prototyping and low volume production. And then the Lens 850R system, which is really our production workhorse and is targeted for larger part sizes and higher throughput. We also offer the Lens Print Engine, which is a modular package that I'll talk about just in a moment that can be integrated in with other platforms. The aerosol jet platforms kind of parallel the lens platforms in that we offer three different kind of turnkey system configurations, the aerosol jet 200 and the aerosol jet 300, and as well we have the aerosol jet print engines for integration into production platforms. From a print engine standpoint, again, what we have done is package this technology, the core elements of our technology, which include the powder feeding technology, the deposition heads, process controls, and toolpath generation. We've packaged this into a modular configuration, which can be added to other platforms. For example, it can be added to a CNC machine tool. And in this one configuration, you are now able to either do additive or subtractive manufacturing in a single platform. And it also allows you to take advantage of existing assets on your factory floor. So this is a new offering that we announced back in February of 2014, so just about a year ago. And it was a result of an America Makes contract award that Optomec was fortunate enough to be a winner of. So this technology is available today. We've sold about 5 of these systems already, and we will be delivering the first hybrid manufacturing system, additive and subtractive manufacturing system to a customer in next month, March. So I'd just like to conclude by summarizing the Optomec difference. Optomec technology enables our customers to not only print parts fully in 3D, but also to print on 3D parts that maybe were produced using conventional manufacturing methods. So this really allows, for example, the ability to add wear surfaces or to repair old components, or even to functionalize plastic parts, as you see on the right-hand side here. Here we have printed an antenna on a plastic cell phone insert that was produced through an injection molding process. So functionalizing plastic parts requires the ability to print on three-dimensional objects. A second difference is that we look at additive manufacturing across the entire product life cycle, from new alloy development all the way through to volume production and product repair. So this life cycle view has required us to really think about how we scale up and integrate the technology into existing manufacturing processes. And I think you'll see that, in fact, we have made quite a bit of progress in that area. And last, we subscribe to an open systems approach. And what this really means is that we believe that 3D printing must coexist with existing processes, and it must integrate into existing machines. And that's why we have embraced a print engine strategy for both printing electronics and printing metals. And other critical aspect of that is that we use commercially available materials so that you as our customer have the ability to source your own materials from suppliers that we have certified. So you can buy your metal powders or your electronic inks from a variety of sources. It provides you a more cost-effective approach, and as well backup sources for your materials as you move into high-volume production. So with that, again, I'd like to thank you for your attention today. If you have any specific questions on our products, please visit us at optimec.com or send us an email at requestinfo@optimec.com. Thank you again. Bye-bye.